Hello everybody, and welcome again to a Let's Study episode. Today we're going to be continuing on the rules for addition, section 2 of chapter 1 of Basic Mathematics by Sergey Lang. We'll be completing the exercises as shown on page 13. So we have problem 1, but we have these exercises in which it is asking us to justify each step using commutativity and associativity in proving the following identities. And we have question 1. We have A plus B in parentheses plus C plus D in parentheses is stated to be equal to A plus D in parentheses plus B plus C in parentheses. So how might we go ahead and prove that this side is equal to that side? And so what we can do is we can use the rules of commutativity and associativity on this left side to make it into the form of the right side. And if both sides are equal, we have proof by identity. A equals A, effectively. 1 equals 1. Okay, so then, how might we go ahead and change A plus B in parentheses plus C plus D in parentheses to equal this side? Well, we can see that if we just think of the ordering of the letters, we have A, B, C, D, and now we have A, D, B, C. So it looks like D and B have swapped places, as well as C and B have swapped places. But let's just make this quite simple. We know by the rules of associativity that we can remove these parentheses from the sum of these integers without causing any issue. So let's go about that. So we can just place A plus B and plus C plus D all together without any parentheses. And we can write that we did this by associativity. So then, well, we have A and D and B and C. So let's put A and D together and B and C together. So effectively what we're going to do is we're going to move or commute D to be in between A plus B. So then we're going to move D across. So A plus D, and then we can add plus B plus C. So we moved or commuted D in between A and B plus C to get the ordering we wanted up here. So now that we did this step, we can justify our step by writing down that we use this by commutativity. Now, this we know is equal to this side, but it's not the same form. So we can't quite say proof by identity because it's not the exact same form. So let's add in those parentheses. And since we know removing them doesn't cause anything, we can also add them in this situation. So we've added these parentheses, and lo and behold, A plus D in parentheses, A plus D in parentheses, plus B plus C in parentheses, plus B plus C in parentheses. A equals A, proof by identity. But we do want to at least write down what we did here. To go from here to there, we use the rules of by associativity. And we can write down proof by identity A equals A. That solves problem 1. So now we have problem 2, where we have A plus B plus C plus D is equal to A plus C plus B plus D. Now read this off again. So we have A plus B in parentheses plus C plus D in parentheses is equal to A plus C in parentheses plus B plus D in parentheses. So we have a similar situation as above, where we have the same groupings of parentheses, but what's in the groupings is different. So we could just quickly, effectively repeat what we did above. So let's remove the parentheses to simplify our problem and allow us to commute everything around without using any sort of special ideas of going in and out of parentheses. If we just remove the parentheses in the first place, then we can move things around in the same sort of space, if you could imagine. So let's do A plus B plus C plus D. And we got there by associativity. Okay. And then let's look at the ordering. We have A, C, B, D. And in this case, we have A, B, C, D. So it looks like all we have to do is swap C and B in this circumstance. So let's do that. A plus C plus B plus D. And we got there by commutativity. Now, it's not shown in this book right now, but we can assume that all of these are integers, because that's all we've been taught with in the book so far. So I'll actually add that. A, B, C, D are integers. I think it's rightful to assume that. I don't think it changes anything, even to real numbers. But irrational numbers might not apply with these rules. I'm not sure. We're going to find out later in the book. Okay, so we have the right ordering, A, C, B, D, A, C, B, D, but we don't have the parentheses. So let's add them back again using associativity. A plus C in parentheses plus B plus D in parentheses. And lo and behold, we have proof by identity. So let's move on to problem 3. So we have A minus B, so we're bringing in some minuses, plus C minus D is equal to A plus C plus minus B minus D in parentheses. All right. So we have differences of signs and we have differences of letter ordering. So we have A and C on the left side, we're trying to get to, and B and D on the right side, which is not what we have on this side. So we do want to move these around, but we also have minuses where we don't have minuses on the left side versus the right side. But similar as above, let's start with just removing these parentheses and using a rule that we've already established. So let's use the rule that we have established. I think I need to go back to find out what rule that is in the book. That would be, it's either N4 okay. Okay. n5. So effectively we have n4 here, where a is equal to minus a. Okay? But it's not quite what I'm looking for. I'm really looking for n5, where we have the minus outside of the parentheses, and it can be distributed in, effectively distributed in to the parentheses. And we're going to use this in a simpler case. So forget the b, and we have minus a equals minus a, but the minus is outside the parentheses. So we can use that here, I believe. So by n5, where minus a plus b is equal to minus a minus b, we're going to apply that rule to our minus b and our minus d. So then we can have a plus minus b plus c plus minus d in parentheses. So we're effectively bringing these into parentheses. So we're using this equation backwards, minus one of the units as well. Now I think that's probably in here is what it's talking about. Effectively, if we take this minus across, we have minus a is equal to minus a in parentheses. Okay, so we're really using n4, I think. So let me correct that. This is my reasoning, flawed or not. Okay, by n4, where we have a equals minus a, in which case we move that minus across. So effectively we can encapsulate our minus a in parentheses. So that's what we're doing. We're going from minus b to minus b in parentheses using n4. Okay. And then now that we've encapsulated the negatives, all we have is positives in relations. And now we can remove the other parentheses that we don't want by associativity. So we can write simply a plus minus b in parentheses plus c plus minus d in parentheses. And then now we can move our ordering around. So we have a, b, c, d, and we have a, c, b, d. So what we need to do is swap c and b. So we're going to swap these. And we're going to do this by the commutativity property of addition. Now that we have them where we want them, what we can do is that we can begin to add the parentheses where we want them and remove them elsewhere. So let's add the parentheses around a and c. And then what we can do is we can effectively remove the parentheses around b and d. So we can add parentheses here, remove them over here, and get this. So this a plus c encapsulating those with parentheses is using associativity, and us getting here is using n4. So we're using two rules in one step. And then now we can use n5, which is negative a plus b is equal to negative A minus B. In this case, we're going to flip this around, and we're going to go from this direction to that direction. So if you imagine we're swapping A and B for B and D, where we have this minus B minus D minus B minus D is equal to minus B plus D. Okay. Yes. So we have A plus C plus minus B minus D. So, I'm not sure this is quite right. I think we're right with our logic, but yeah, I'm not going to throw out big words like that without confidence. Effectively, I think I need to use associativity and then N5. So what we did here instead is we used associativity. And that's actually all we needed to use. Yes, I think so. Okay, I think that answers question 3. Let's move on to question 4. We have A minus B plus C minus D is equal to A plus C in parentheses minus B plus D in parentheses. So then, check if I wrote down the correct. Okay, so we have A minus B in parentheses plus C minus D in parentheses is equal to A plus C in parentheses minus B plus D in parentheses. So let's simplify with using associativity. And I believe, what did I use before? N4. So with associativity and N4, where minus A is equal to minus A in parentheses, we can get A plus minus B plus C plus minus D in parentheses. And then we can reorder it. So we can commute and swap B and C. So A plus C plus minus B in parentheses plus minus D in parentheses. So this is by commutativity. Okay. And then we can group A and C together by associativity. And that will be A plus C plus minus B plus minus D. And then by N4, sort of in reverse, we can remove these parentheses and take out the negatives. So we have minus B minus D. And then by N5, so how did I write N4? N4 minus A equals minus A. And by N5 we have N, is it, I should write down these N's, these rules. Yes, alright, I was right. Alright, we have minus A plus B equals minus A minus B. So in this circumstance, we see this, and what we can do is we bring that over here. So effectively, what we can do is we can go from here to there. So we have minus B plus D. And lo and behold, A plus C in parentheses, A plus C in parentheses, minus B plus D in parentheses, minus B plus D in parentheses. So we have proof by identity. So then we can move on to problem 5. Where we have A minus B in parentheses plus C minus D in parentheses is equal to A minus D in parentheses plus C minus B in parentheses. So again, we have a different ordering, but let's just sort of follow the exact same procedures as we have been before. So by associativity and N4, where minus A is equal to minus A in parentheses, we can remove parentheses where we don't want them for now and add them where it simplifies everything to addition. So we have A plus minus B plus C plus minus D in parentheses, minus B in parentheses as well. So then we can reorder it. We want AD, CB, AB, C, D. So we want to get D and B need to swap. So we're going to swap B and D. And we can use that by commutativity. So we have A plus minus D plus C plus minus B. Okay? And then we can, by N4, minus A equals minus A in parentheses, we can use the reverse of this to go from parentheses to no longer in parentheses. And so we can go from addition to subtraction or additive inverse with the minus signs with both B and D. So we have A minus D plus C minus B. Okay? And we got what we have up here in order as well as in signs, but we don't have the parentheses. We can easily add them by associativity. So A minus D in parentheses plus C minus B in parentheses, just as we have up there. So this side equals that side. Changing from this to there, using these rules, we have both sides equating to each other. We have now proof by identity. Where A equals A. finished problem 5. So let's move to problem 6. We have A minus B plus C minus D is equal to A minus D plus C minus B. I always get messed up with parentheses. I sort of read them as, hold on, let me move the light. So I'm casting less of a shadow. Can I do that even more? There we go, even less of a shadow. That's an improvement on my writing, so you can see what I meant. So I write a parenthesis, but I skip writing a C because it looks like a parenthesis. I have that problem visualizing it. Okay, so we have A, B, C, D, A, D, C, B, different ordering. So let's sort of just follow this, almost a continuation. This is sort of a little excessive, going in over and over and over again using the sort of the exact same procedure. Alright, so by associativity, and N4, where negative A equals, negative A minus A equals minus A in parentheses. So we can get there by A plus minus B plus C plus minus D. So what you can imagine here that we're doing is we're putting minus B into parentheses as well as minus D, and then we're removing the outside parentheses. So we're doing 2 steps in one, but we're using 2 rules in one, so it's a little complicated. I'm not sure if I should write separate steps for both, but I think it's sort of self-evident. It should be simple enough to visualize from how you got from here to there. Should be. Maybe it's just me. Maybe I'll get docked points by some magical person. I don't know. It's not exactly like I'm turning this in. I'm just doing this for myself and for you. Okay, so we have the wrong ordering, A, D, C, B, and we have A, B, C, D. So what we need to do is we need to move these around. So it looks like I can get there by moving B over to the right, to the end. So we will commute that over to the end. So A plus C plus minus D in parentheses plus minus B in parentheses. No, that's not quite right. That's not quite right at all. We needed D and B to swap. That's what we needed. I think I was thinking of an earlier problem that we just did. So we have A plus minus D plus C plus minus B, with minus D and minus B in their own parentheses. Okay, A, D, C, B, A, D, C, B. So we got the right ordering. Okay, so then this will be quite easy. So we have the parentheses inside. What we can do is, well, simply take that out of the parentheses. So let's follow N4 in reverse. So by N4 minus A equals minus A in parentheses, we could do A minus D plus C minus B. No more parentheses. So we have the ordering A, D, B, C, D, A, D, C, B, A, D, C, B, and we have the right minus signs, A minus B, A minus D, and we have C minus B. But we don't have the parentheses that we want. So let's use that associativity rule. Associativity to add those parentheses that we need. A minus D plus C minus B. Okay. A minus D in parentheses, A minus D in parentheses, plus C minus B in parentheses, plus C minus B in parentheses. We have the same on the left and the right, therefore proof by identity. A equals A. No, let's move on to problem 7. Where we have A minus B in parentheses plus C minus D in parentheses is equal to, we're getting complicated on the other side now, to minus B plus D in parentheses minus A minus C in parentheses. Okay, so we're getting complicated on the other side now. But we shall follow the exact same sort of procedure as we have before. So by associativity and N4, minus A equals, in parentheses, minus A. We're going to separate these into like sort of individual components separated only by addition. So we have A plus minus B plus C plus minus D. Okay? Then let's get the correct ordering we want. B, A, A, C. Okay, so B and A, swap those around. That doesn't make sense. I must have wrote this down wrong. Is that D? D. Need a little higher on that. My A's look like D's. Fighting the urge to make a D's joke. Really fighting. And succeeding. Let's move on. Okay, so we have A plus minus B plus C plus minus D. Okay, that's good. Okay, and so the ordering is B, D, A, C. So let's get that ordering by commutativity. Commutativity. Alright, so B, so let's do minus B plus, we want the D, so minus D, and then we want A and C, so plus A plus C, and here we are. But we want to get to both of these. So what we can do, I think first we need to do is we actually use N4 again. So sort of like this N4 rule I'm continuously using is sort of like packaging this minus sign into a little packet that we can later unpack later on. But it makes it easy to commute with when you have this parentheses sort of encapsulating this negative number, so you can move it around without the idea of like that negative number being distributed in or out. So that's what I'm doing here. Maybe that's a bad strategy, maybe it's a good strategy, I don't know, but I think I'm getting correct answers. So we're going to continue on with it. But I might be wasting steps because I'm using N4 and then I'm using N4 again later on. So I might be wasting my time. So it might be more efficient not to even use N4 and just use classic associativity. Might be. But I like to encapsulate them. I don't know, makes it a little easier to work with negative numbers. Well, minus some value. Okay, so then we're going to use N4 again, where minus A is equal to minus A in parentheses. We're going to use the opposite of this. So we're going to go from parentheses to no parentheses with B and D. So we're going to take them out. We're going to uncapsulate them. We're going to break them out of their little capsules. So minus B minus D plus A plus C. Okay? And then I believe what we have to use N5, which, grab the sheet from earlier. N4, N5 right here. minus a plus b equals minus a minus b. So let's do that. At least by n5, where we have minus a plus b is equal to minus a minus b. Alright, so what side looks like what side? Okay, so this looks familiar. Minus b plus d minus a plus b. Okay, so replace b with a, or we'll replace a with b and b with d, and then we have, well, what we have up here, and we can get what we have on here side. So this side can be equal to that side by using the rule of n5. So what we can do is we can sort of take these out, and we got b plus d as we want up here. Okay, and also we could do a similar thing down here, I think. I'm not sure if I can just directly use this rule. Not sure if I can. Sort of we can extract like a negative, a minus, out of a and c and place it outside. Now I want to just do this. But does n5 justify my action in taking that from here to there? I think it does, but how might we prove that? Okay, here's what we can do. We can take n5, and then we can sort of move that negative to the other side. Well, no, then we just end up with a plus b equals a plus b. That's not really, that's just identity right there. That's not useful. It's not that it's wrong, it's just not useful for us. It's really hard to write with the camera. Sort of, well, we're following... Here we are. We're actually using... Okay, so we're using n5 here. Okay, but we're really using n4 over here. Okay, so you can see this. We can replace a with a plus c. So we have minus a equals minus a, where we can say a is equal to, well, a is not a good letter to use in this circumstance. So let's swap a for, say, x. Where this x is equal to a plus c. Okay? So then, what we can have is a plus c is equal to parentheses minus a plus c. Then we could distribute that in. Minus a minus c. Okay, and then we can, I believe, we could just sort of bring this multiple, this minus over, where, oh, okay, I think I get it. Do I? If you look up here, a plus c minus a plus c. This is effectively n4. No. I'm a bit lost, to be very honest. How might I describe what I'm doing in a justified manner? I think I can take a simpler approach. So let's just separate this. So one step. So we just did n5 over here. So keep this a plus c. And then by, I believe this by n4, where we have a is equal to negative a. Is that n3 then? No. Well, it's a different a. n3. n3 is a plus b equals 0. What have I been writing this whole time? I keep writing it n4. That's not right. That can't be right. Okay. Oh, that's okay. This is how we can do it. It's rather interesting. We will prove a different proof. We'll just do it and then prove it. Alright, so let's prove that we can get a plus c, well, plus a plus c to equal minus a minus c in parentheses, just by, well, effectively doing a little problem within a problem. So let's say it. A plus c is equal to minus c in parentheses. Okay? So we can have, using n5 on this side, by n5, we can distribute that minus in, so we have minus a and minus c. And then we know by n4 over here, a equals minus a. Sort of the minuses cancel themselves out, and then we get just the positive. That's equal to a plus c. Okay. For both cases. So a plus c equals a plus c, proof by identity. So then we could do the same down here. So by this rule that we just applied, with this relationship that we have applied, where we proved using n5, this is a proof. We can use that here. So minus b plus d. Minus a minus c. Okay, so minus b plus d in parentheses, minus b plus d in parentheses, minus a minus c in parentheses, minus a minus c in parentheses. Okay, so proof by identity, we have solved this problem at last. So I think I wrote n4 properly in the past. I'm trying to get it sort of how I got there. I think I did this. So I had n4 here, where I started with the original text. Okay. Down here. And then what I did is I moved it around. So I sort of moved that minus to the other side. And then that is what I've been using beyond that. So it's like I made a modification of what the book wrote, and then I used my modification as reference to the book. But the book doesn't write this, it writes that. I made this and then assumed that this was n4. and continued on with that. So that's how we got to other places. Now these are equivalent because I use the rules of the minus signs effectively, because I'm allowed to move these minus signs. Using N3. Not sure how I'm justified right here. Well, I think it's for... Oh, it's sort of proving. Oh, this is proving because of N3. A plus B equals 0. Effectively. I think. Let's move on to problem 8. And ignore the growing feeling that I don't know what I'm doing. Well, yep. Okay, let's work on problem 8. So, we have, in parentheses, we have x plus y, in parentheses, plus z, and a big set of parentheses, plus w. And this is equal to x plus z in parentheses, plus y plus w in parentheses. So we have new letters, x, y, z, w. Alright, so we have x, y, z, w, and we have x, z, y, w. So we have a different ordering. It looks like we need to swap y and z around. So we can't swap them around until they're on the same sort of playing field. So let's do that with associativity. Associativity. So we can use that in several steps. So x plus y, we can do x plus y plus z in parentheses plus w, and then by associativity again, just not to complicate things. No, we're trying to get rid of those parentheses. Bring them back. We have x plus y plus z plus w. Okay, and now we want to swap our z and our y. So we're going to use the commutativity property. So we want to swap these around. So we have x plus z plus y plus w. Okay, so we have x, z, y, w, x, z, y, w, but we have the correct ordering, but we don't have the parentheses. We can add those in again with associativity. X plus z plus y plus w. And we have the same on the left as we do now on the right. This is proof by identity. A equals A, where A equals x plus z in parentheses plus y plus w in parentheses. So we have problem 9. X minus y in parentheses minus z minus y in parentheses is equal to x plus w in parentheses minus y minus z. Okay. So we have a different ordering. So with the rules of by N4 and associativity, we can remove these parentheses and encapsulate our negative numbers. So we have x plus minus y, n4 being minus a is equal to minus a in parentheses, which is a equals minus minus a. Ooh, but it's a little complicated right here. So that's how we can get there with that. So we can get there and not do the other ones yet. Here we are. We have the minus sign outside the parentheses. So what we could do is we could distribute that minus sign into these parentheses using, I believe, n5. Where we have minus a plus b is equal to minus a minus b without the parentheses. Okay? So effectively we're going to go from there to there. So, but we can't do that yet because we have a plus sign here and we have a minus sign here. So we need to package that up so it looks like this side so that we can apply the rules. We'll apply this. Sort of one-to-one. So we can't do that yet. So we can use by n4 really quick right here. We have minus c plus minus w. Okay, so then you use by n5 right here, where a equals z and b is equal to negative w. Okay, so then we can have x plus minus y, bring that down, and then we can have minus z minus minus w. Okay, and then we can use with by n4, we can remove these. We can add parentheses here to encapsulate this minus z or z, and we can remove this minus here by sort of canceling them out. Sort of x plus minus y in parentheses plus minus c in parentheses plus w. Okay, so we've extracted or distributed this minus sign into the equation using n5 after we packaged this side of the equation up and nice with n4 to look like n5 so we can apply it. And now we've gotten to a quite simplified aspect of all of our individual components on a addition sort of single plane. So we want x, y, x, w, y, z ordering. So x, w, y, z, so we need to bring in w over here. So we use that with commutativity. So by commutativity, x plus w plus minus y in parentheses plus minus z in parentheses. Okay. And this is simple right here. We need to get these into some parentheses, so we could do that with associativity. X plus w. And just bring this down. We didn't touch it. All right. And then by n4, we can take these minuses out and their parentheses to get x plus w in parentheses minus y minus z. Okay, and then we can see that we have the same on both sides. This is proof by identity. Let me use up this sheet. This is always a cool imagination that if you buy paper and pencils, stationery supplies, erasers. Well, sort of don't want to use up erasers. But if you buy paper and pencils and you use them up to their fullest, you've most likely gained so much more than the cost of the paper and the pencil. So it's one of those resources where the more you use it up, the more you're benefiting. I find that to be a really cool concept. It's like you want to run out of paper. You want to run out of your pencil, your pen. Now, you don't quite want to run out of your eraser because that means you're making mistakes. But it's sort of, it doesn't apply to erasers, but it does apply to your normal supplies. What problem were we on? 9. So now we're on 10. I believe 10 comes after 9. Oh, so let's write number 10 up here. So we have x minus y minus z minus w in parentheses with x minus y in parentheses. So that is equaling x minus z in parentheses plus y, w minus y in parentheses. Okay, so how shall we do this? Easy peasy. Let's use N4, where we have a is equal to minus a, which is minus a is equal to minus a in parentheses. Okay, so how we can do that? We can, well, get these minuses inside these parentheses in their own little capsules. X plus minus y minus z plus minus w. Okay? And then, now that we have these as sort of a plus b minus, oops, missed a parenthesis, we can apply the rule of, we can do associativity here. So let's just do that. So x plus minus y in parentheses. So we just get rid of that extra, well, get rid of that major parentheses. And just bring down what we're working with from above. Okay, and then we can use by N4 minus a plus b equals minus a minus b, where a, is equal to z and b is equal to, in parentheses, minus w. And using that, we can distribute in this minus sign. Just distribute it in, distributing meaning that we're getting rid of these minus signs. Minus c minus w in parentheses. Okay. And then by N4, a equals minus a in parentheses, we can make w positive. And by N4 minus a equals minus a. In parentheses, we can encapsulate z, so x plus neither y minus, not minus, we want a plus, minus z in parentheses plus w. Okay, so everything's nice and ready to be moved around. And we want the ordering x, z, w, y. Alright, so let's get that. X plus minus z in parentheses plus w plus minus y in parentheses. Okay, and this is all with the commutativity properties of addition, alright, So then we can easily take this out. So if by n4 minus a is minus a. Oop. Minus a is equal to minus a in parentheses. We can take these out, so decapsulate them. Okay. And now we have the correct ordering and the correct signs, but we're missing some parentheses. So we can just add them back in with associativity. So we have x minus c in parentheses plus w minus y in parentheses, which is the same as what we have above. This is now proof by identity. Alright, and we can move on to problem 11, where we want to show that minus a plus b plus c is equal to minus a plus minus b in parentheses plus minus c in parentheses. Okay, so I know how I'm going to get there. Okay, so let's use by associativity. Let's group b and c together. So minus a plus b plus c in parentheses. Okay. And then what we can do is we can do by n5 minus a plus b is equal to minus a minus b. Okay, and where this is where our a in this circumstance is equal to a, and this b in this circumstance is equal to b plus c. Now very obviously we should be using different letters for this, because this a is a, like, okay, that makes sense, but that's not because a is a, it's because of the positioning. So if this a in that left hand side and this b plus c as one thing on this right hand side can be used to produce this form of that form, simply because it's by form, not because it's using the same letter. So in reality, what I should do is replace a and b up here in this n4 or n5 such that it doesn't share the same letters. So let's try x and y, because they're not being used above already. So let's use x and y. They're just placeholders anyways. Okay, so that makes it a lot cleaner. Okay. So then, with this and this, we can do that down here. So by this rule, we can get to here. We have minus a minus b plus c. Okay? And then we can use n5 again. Or minus x plus y equals negative x, negative y, where in this case, x equals b, y equals c. Okay? So then we can distribute this minus sign in. So minus a minus b minus c. Okay? Then now that we got here, we can use n4, where we have a equals minus minus a, where we can have minus a equals minus a in parentheses. So effectively we can package that up in parentheses. So we have minus a plus minus b plus minus c in parentheses. And that's what we have from here these both sides are the same. Minus a plus minus b in parentheses plus minus c is equal to minus a plus minus b in parentheses plus minus c in parentheses. So this is proof by identity. Alright, and it looks like we didn't use that much of the page, so we can actually do 2 problems on the page. Get ready for physics and calculus, where your problems might take up 5 pages or more. I think the longest equation I did, now it's not because it's a really hard problem, it's probably because I was less than smart with how I was performing the problem, but I think I had a 12-page equation in my modern physics class. I didn't even accomplish that class. I did not pass it. I think I withdrew. Okay, so we're not there yet. So let's 12. Let's show that minus a minus b, and that was quantum mechanic questions. Assuredly, I was doing it wrong. I don't even think I have the surviving notes from that. Okay, so question 12. Show that minus a minus b minus c in parentheses equals minus a plus b plus c. Okay. All right, so sort of the same as above, but we got to get there. Okay, so then let's have minus a plus b plus c. Is that possible? Hold on. Okay, I'm back. I'm just going to erase this and try to pick off where I started. So I'm trying to do what? Not quite sure. Yes, I'm trying to get this to be an addition. Minus b minus c. So we... Oh, well, that's easy. We use n4. Or a equals minus a in parentheses minus a equals minus a in parentheses. Oops, sorry, right here without that extra parenthesis. So then what we can do is we can have plus minus b, and we have plus minus c, both of those in their own parentheses. And then by associativity, we can have, let's say, plus minus b in parentheses plus minus c in parentheses. Okay, and then now we have this minus sign outside. We can use n5, where minus x plus y is equal to minus x minus y. In this case, where x equals a and y equals, in parentheses, minus b in parentheses plus minus c in parentheses. Okay, so we can remove these outer parentheses. So minus a minus b in parentheses plus minus c in parentheses. Okay, and then by n5 again, minus x plus y is equal to minus x minus y. Okay, and this is where x is equal to minus b in parentheses and y is equal to minus c in parentheses. So we have minus a minus b in parentheses minus c in parentheses. Okay, and then we can do by n4 minus, no, this is a equals minus a. Getting a little tight. So minus a plus b plus c. So we'll have these minuses cancel out. Okay, and then we have minus a plus b plus c minus a plus b plus c, proof by identity. Okay, new sheet, so we can move on to the next problem. So we were on 12, so now we are on 13, lucky number 13. 13. Okay, let's show that minus a. Oop. Remember, the quickest way to be incorrect in your work is to write the problem down incorrectly or misunderstand the question. I think both go hand in hand. Show that minus a minus b in parentheses is equal to b minus a. Okay, well, that's quite easy. So let's use by n4, a equals minus a to minus a equals minus a in parentheses. Encapsulate the minus, so we have minus a plus minus b in parentheses. Okay, and then by n5, or minus x plus y is equal to negative x, negative y, and this is where x is equal to a and y is equal to negative b in parentheses. So we could distribute that negative sign into our equation. So we have minus a minus b in parentheses. Okay? And then what we can do is then we have minus a. We use n4, where a is equal to minus a. We have plus b. Oop, no parentheses remaining. Okay. And then we can use n4 to encapsulate negative a. So if a equals minus a. Well, oops. Well, actually, yeah, we can use a. Minus a is equal to minus a encapsulated b. And then we can use by commutativity, because we have up here BA and we have AB. We want to swap these around so we get the correct ordering. By commutativity, we can have B plus minus A in parentheses. And then we want to remove the said parentheses by n4. So minus a equals minus a in parentheses. So b minus a. B minus a is b minus a, proof by identity. Okay. Then we have problem 14. Solve for x in the following equations. Like I say, I have glass right here in my hand up against just paper for insulation, and the glass really cold. I think the house is just cold. Let me turn the heat up. Okay, so they brought it up by 2 degrees, so it should warm up the house, which will warm up the glass, which will warm up my hand. Looks like just good old friction. Or, even better, nice cup of coffee. Well, my coffee's cold. Let me grab a new cup of coffee. It looks like that pencil has no shadow, like no shadow at all. Almost looks like it's floating there. We got a little bit of a shadow on this edge. It's like edited in. I got a nice hot cup of coffee. I warmed my hands up. It's cold in the house. I had it at like 68. Normally I like to keep it at like 69 for the lulls, and 70. A little higher. Sometimes 72 if I really don't want to be cold at all. It's getting a little hot. Okay, off topic. Oh no, my leg came out. Okay, new piece of lead. Alright, 14. Solve for x in the following equations. So it looks like from problems 14 to 21. Yep, 14 to 21, we'll be dealing with solving for x. Ooh, a new problem that we've never ever seen before, of course. Alright, so 14, we have -2 plus x equals 4. Okay, well that's quite easy. So what we could do is add 2 to both sides. Okay, so 2 minus 2 plus x equals 2 plus 4. Alright, 2 minus 2, 0, plus x equals 6. And then by and 1, where 0 plus a is equal to a plus 0, which is equal to a, where a is equal to x in this circumstance. We can get rid of that 0. That 0, poof, out of existence. And then we have 2 and 4, 6. So if we have a number line, here's actually a proof of addition. Say we have our number line right here. Okay, we have 2 right here, and then we're going to move 4 positions to the right. 1, 2, 3, 4, 6. Okay, so 6. So for 14, we have x equals 6. Now, is there a rule that describes this that we can add 2 to both sides without changing the equality? I'm just going to assume that we can. Obviously, it's quite an easy assumption that you can add 2 to both sides of the equality, and since they both increase the same amount, it doesn't change the fact that they're the same. If they are truly one and the same. It won't affect it. Either the original statement is true or it's false, but we can add both. We can add a positive integer to either side, or minus integer to either side, and it will not change our inequality, whether it be true or false. Our equality by... Okay, so x equals 6. Nice and easy. We can use the centimeter side next time. Okay, so that's 14. Let's move on to 15. These problems are going to be a little easier than even the ones above, I assume. 2 minus x equals 5. Okay, let's get x on its own. How might we do that? So let's, in this case, add x on both sides. Okay. 2 both sides. So then we have 2 minus x plus x on this side equals 5 plus x on the right side. Okay? And then we have minus x plus x. Okay? And that we can get is 0 by which rule can we do that with? Okay, so effectively, since x is equal to x, what rule is it? Okay, it says n2. Easy peasy. It's right in the book, right here. And this is by assumption. So we haven't even proved this n2, but we're going to just use it. And also, we're using the other one, this right side. Minus a plus a equals 0, and this is where a equals x. So then we have 2, well, effectively plus 0. Yep. Well, actually we need to, we're being ultra precise here. Ultra precise. Obnoxiously precise, I imagine. We're already an hour and 20 minutes into this. So let's get this to addition. A plus, ugh, my neck. Ouch. Oh, it's just yeah, associativity plus minus x plus x. Okay. So let's cancel that and just use by associativity. And then by n2 minus a plus a equals 0. So that would be 2 plus 0 in parentheses. 2 plus 0 by associativity. And then by n1. Where's n1? By n1, a plus 0 equals a, where a equals 2 in this circumstance. So we have 2 is equal to 5 plus x. Okay. Then by additive inverse of 5 to both sides. These papers don't stick to alignment. Very annoying. My hands are cold. Alright. So 2 minus 5 is equal to 5 minus 5 plus x. Okay. So 2 minus 5. I can't even show it here. Stupid number line. I think we can all assume that 2 minus 5 is minus 3. And 5 minus 5 is 0 plus x. And by n1 minus 3 equals x. X equals minus 3. Okay. This is problem 15. Let's move on to problem 16. X minus 3 equals 7. And let's add 3 to both sides. x. Wait, isn't there, there's a thing here. No, it's later on. It's way later on, I think, in the book, where it makes this a lot easier to imagine. I'll deal with that when we get to it. Effectively, it's a better way of describing what we're doing. So, minus 3 plus 3 equals 7 plus 3. Alright, and that will be x minus 0 is equal to 7. No, not 7 plus 3. That's just do addition. That'll be 10. X equals 10. Now we don't have a specific rule that says subtracting by 0 is the same. I guess we're just going to take that as assumption. Or by n1, x minus 0 is equal to 0 minus x. Oh, that's not true. It can't be true. If we don't move x, x remains the same. I don't think there's a specific rule in the book that we can reference. But adding or subtracting 0 makes no change to the value that we're doing it to. So I'll write my own n 1.1 where a minus 0 equals a. I don't know, plus 0 equals a. Not bad. Just making up rules now, by assumption. Alright, 17. We have minus x plus 4 equals minus 1. Alright. So let's get x to the other side as well as removing its minus because we want x by itself. Nice and easy. So let's add x to both sides. Minus x plus 4 equals minus 1 plus x. X's cancel here. 0 plus 4 equals minus 1 plus x. And we can add 1 to both sides. And use n1. So we get 4. And then we get 4 plus 1 is equal to negative 1 plus 1 plus x. That equals 5 equals 0 plus x. 5 equals x by n1. And then x equals 5 for problem 17. Problem 18, we have 4 minus x equals 8. And so let's add x to both sides. So 4 minus x plus x equals 8 plus x. 4 minus 0 equal to 8 plus x. And 4 equals 8 plus x by n 1.1 by assumption. A minus 0 equals A. Okay. And we want to subtract additive inverse 8 to both sides. So we have 4 minus 8 equals 8 minus 8 plus x. So then we have minus 4 is equal to 0 plus x. And by n1, we have negative 4 equals x. And we swap that around. X equals minus 4, answering our problem 18. Then we have problem 19. We have minus 5 minus x equals minus 2. So we have a minus x on this side, but yeah, we have a minus x on this side, so we can just add x to both sides. So we get a positive x on one side. Okay, so negative 5, not negative 5. Well, it is negative 5, but minus 5 minus x plus x equals minus 2 plus x. And that will equal minus 5 is minus 0. Is that plus 0? Minus 0 plus 0, I'm not quite sure it matters. Minus 2 plus x minus 5, this is by n1, 0.1, a minus, so if anything, minus 0 is the same by assumption. Then we have negative minus 5 minus 2 plus x, well, equals 2 minus 2 minus plus x. And so let's add 2 to both sides. Minus 5 plus 2 equal to minus 2 plus 2 plus x. And that how we have minus 3 is equal to 0 plus x, which by n1 by assumption. A plus 0 equals A. We have minus 3 equals x, and swap that around, where by, what is this? Is this actually a 1? I don't know if it's a rule by commutativity. No. I don't know if there's a rule specified that you can whip around a equal sign. We just assume that we can do it. I don't like doing that. I end up with a very ugly equal sign. X equals negative 3 for the answer for question 19. Sheet of paper, and that paper took a ride. It flew away. 2 more problems, and then we're done. We have problem 20, where minus 7 plus x equals minus 10. Okay, so let's add 7 to both sides. Okay. So we have negative 7 plus x equals negative 10 plus 7. And then we have 0 plus x equals -3. And then we can have x plus 0 by commutativity. And then by n1, where a plus 0 equals a. Actually, we could have kept a as 0 plus x, because n1 also has 0 plus a written in it. Yeah. So I didn't have to do that step, but we could do 0 plus a. You have x equals -3. Easy peasy. And then let's go to 21, our one and final program exercise for this section. -3 plus x equals 4. Okay. So, well, we have positive x on one side, so we want to isolate it by removing the 3, bringing it over to 4. We want to just remove the 3. And how we can do that is we can get rid of it by adding 3 to it, as well as on the other side to make sure that this equality stays equal, or at least unchanged. So by adding 3 to each side, we have -3 plus 3 plus x equals 4 plus 3. And we have 0 plus x equals 7. And then by n1, we're 0 plus a equals a. X equals 7. Okay. And those answer all of our exercises in section 1 and 2, or after section 1 and 2 of chapter 1 on numbers, with section 1 on the integers and section 2 on rules for addition. We were able to apply those rules that we learned, such as commutativity. Let's do a little review, might as well. So what we read in the previous video is we began chapter 1. We read through section 1 on the integers, where we were introduced to the positive integers, 1, 2, 3, 4, and continuing. We add the 0 to get natural numbers, and then we add negative numbers, negative integers to get the integers, and then we introduce our beginnings of rules. So we have n1, where you can add 0 or add to 0, and you'll only get what you added to it, or what is being added by 0. And then with n2, adding the negative of something to itself of its positive is 0. So the minus and the positive are equal distant from the center. And if you add them two together, you always meet at the center, no matter if you go from either direction. They are symmetrical in sense. And then here we have this section, which I very much like, where it sort of gets around the sort of stigmatism of calling things that have a minus sign in front of them as negative a, because negative a means that like this value is negative, but in reality a could be -1 in this circumstance. So minus -1 is actually +1. So you can't quite call this negative a, because it's more accurate to say it is minus a, because we don't know what a is. It could be a negative number, and then therefore this could be positive. So saying negative a is not correct. And also, if you are saying minus a, you can also call it an additive inverse, because we're doing the opposite of adding. Instead of going right on the number line, we are doing the inverse. We're going to the left. And then we get introduced to our rules of addition, where we have commutativity. Effectively, we can add integers in any order, and it will not change the relationship. Euler's sum. And then we have associativity with integers, where we can have parentheses, and we can add them in any order effectively, changing how or where we add first. But in the end, if it's a sum of integers, you can do it in any order. And then we got treated to the third rule, where if a and b are equal to 0, so if they cancel themselves out, then b must be the opposite of a, and a must be the opposite of b. And then we get shown the rule N4, where effectively we are shown that minus signs in even pairs cancel out. So a, minus a, and minus minus a, minus minus a equals a. So long as we have an even number of minuses, the original value doesn't become negated. But the inverse is true. If we have an odd number of minus signs, the final value will be negated. Not that it will be negative, but it will be negated. So whatever it is, if it's positive or negative, it will now become, if it was positive, it will be now negative, and if it was negative, it will now be positive. It will reverse. Then we are treated to N5, where it's sort of, I'll call it the distributive property of the minus sign, or negation. And so effectively we can take this minus sign and bring it into this parentheses, applying it to each integer in the parentheses. So we have apply minus a to a and minus to b, so we have minus a minus b. And then we have here a very simple explanation that's almost too simple to replicate, or not replicate, but just to it's not even worth bothering talking about, but I will talk about it as well, since the book talked about it. If a and b are positive integers, the only result that they could have being added together is a positive integer. So if you have positive and positive, they can only go that way. They can only be positive. And the opposite is true. If a and b are negative, if you add them together, they're going to go to the left. They're going to go even farther negative. Then I think that's the last bit of nugget of things I want to review for this little section. Okay, so that concludes section 1 and 2 of chapter 1 on numbers, exercises. And next up, we will be learning about cancellation law for addition, and we're moving into the rules of multiplication in the next video. Thank you for watching. Goodbye.